As Joel said, I'll be talking about RiakCS, and I'm not going to talk so much about how it works, but more about some techniques that we use to make it easy to develop, easy to change, easy to debug, et cetera, stuff like that. As you said, I'm Bryan. I'm hobbyist on Twitter, and that will help you if you would rather have the PDF slides. I just tweeted a link to them, so you can go download them. But you can also feel free to throw tomatoes at hobbyist. So I will give a little bit of a description of what RiakCS is, because it'll help you understand the rest. RiakCS is it is Apache 2 license, but it is an Erlang application that sits in front of a Riak cluster to expose an interface that is almost exactly the same as the interface to Amazon's S3, their distributed cloud storage system. We developed this partly because people really like S3, and they really want to be able to host their own, so they're not reliant on Amazon's infrastructure, beholden to Amazon's pricing, whatever. But also because Riak itself, without RiakCS in front of it, doesn't do well with really large blobs. So if you wanted to store a 4 gig, 4 terabyte file, you would need to break it up to store in smaller bits of Riak objects. And that's exactly what RiakCS does, is it takes a large file, breaks it up into small bits. By default, I think they're a megabyte in size, and stores those in Riak, but then presents an interface to the user that is just the file. So the actual end user, the consumer of the S3 interface, doesn't have to know about this. As I said, it's Apache 2 licensed. We open sourced it in March. So everything I'm about to talk about, you can go to GitHub and read the code and find out whether or not I was lying or learn to do it in your own application. Some of the dependencies we use are Web Machine. We use Web Machine for the HTTP interface because it's vaguely RESTy. We use Logger to tell what's going on. We use RiakC. RiakC is a Erlang client for Riak. It speaks to Riak over protocol buffers. We use Poolboy to pool those clients such that we're not spawning infinite number of clients to do stuff. Druid is a UUID creator. It hooks up to a native package to produce UUIDs, which we use, and I'll explain in a minute. Node packages Erlang applications really well, so you can deploy them in places with nice start scripts and debug scripts and that kind of thing. Folsom, if you went to the tutorial, is all about gathering stats. It's really handy, and it does much better stats than what you would do on your own. Instead of just moving average or whatever, it has geometric averages and Courtois and all this kind of. It's great. Sext is it's like term to binary, but the binary you get out the other end sorts exactly the same way as the term would have. So you can have a pile of binaries and sort them, and they come out just like sorting those terms would have done. And then Eeper is another way for us to look into a node and figure out what's going on inside. So that may be useful to other applications you might be developing. But as far as RiakCS goes, this is kind of the high-level view. So if you view all of those orange RiakCS, all of those orange Riak boxes as a Riak cluster, those nodes are all talking to each other all the time, just like a regular Riak key value store. The yellow RiakCS boxes up at the top all operate completely independently from each other. So each RiakCS node does not need to know about any other RiakCS node. As far as it's concerned, it's the only one. It does not store any data locally. It stores all of its state in the Riak cluster. And what this means is you can start up a RiakCS node, take out a RiakCS node at any time you need to. You don't have to plan the deployment or anything. If you need more front-end capacity, you spin up another RiakCS node. If you need to save money, you take down the RiakCS node and let people hit the ones you already have up. The one other box on here is that green box that says stanchion on it. There are a very few pieces of data in RiakCS that have a global name. So across all users, only one user is allowed to use that name at any time. That's usernames and bucket names. So when you're uploading files to RiakCS, you put files in buckets. They're kind of like directories, but it's a one-level hierarchy instead of a nested file system. So we use stanchion to serialize the creation of those objects, such that we can guarantee that only one user claims any of those names at any time. Stanchion is just like the RiakCS nodes. It does not store any data locally. So despite the fact that it is a single point of failure, if it fails, you just throw up another one, and it's all good. You don't have any transfer over time, anything like that. Despite the fact that it fails, you can, or it might fail, you can just bring a new one online without any hot swap failover problems. So some general topics I'd like to talk about that really affected how RiakCS was created and is malleable and that kind of thing are immutability, backpressure, web machine in general, EQC 503, and records. And just very briefly, immutability you should all be familiar with if you write Erlang. That's that thing where once you create a data structure, you don't change it. You create a copy. Backpressure is just, preventing some thing that is sending you stuff from overwhelming you. Web machine, like I said, is the HTTP tool. What I'm going to talk about is how we had to modify it a little bit because presenting the S3 interface is just a little bit awkward through web machine. EQC stands for Erlang Quick Check, which is an awesome testing framework that you should really consider using, and I'll show you why. 503 is the HTTP status that says the service is not available. And you might think it's odd for me to talk about that, but it relates to backpressure, and we'll get to that momentarily. And then we're also going to talk about records, everyone's favorite subject, despite the fact that maps are coming soon, which will be a lot of fun. So we'll start with immutability. Like I said, you should be familiar with immutability. This is the thing where, once you create an Erlang data structure, a tuple or whatever, you don't change it. If you're going to change some element in it, you create a new tuple with the new element. And we use this in Erlang, right, because it prevents certain kinds of bugs. Well, we wanted to use it in RiakCS for the same reason. We wanted as much RiakCS data to be immutable as possible, just to avoid the bugs that mutability could bring in. So I was talking about how RiakCS breaks up a file and stores all the chunks of it. Besides the chunks, it also stores what we call a manifest. The manifest is sort of, you might think of it as the root of the tree of chunks. It stores the name of the file and the length and who created it and the access control list. It's basically all the metadata of the file. The other thing it includes is a thing that we call the version. The version is a generated UUID. That's what we use that Druid tool for. Every time you start writing a RiakCS file, we generate a UUID. That UUID is what we use to name the blocks that you have written into that file. So you start writing a file, we generate a UUID, and every block you write contains that UUID in the key of its Riak object. So the first block is that UUID -1. The next block is UUID -2, -3, etc. What this means is when we start writing, if we overwrite the file, we generate a new UUID. So we start writing completely new blocks. What this means is when you go to read a file, you look up the manifest, and it has one UUID in it, the most recent write. So when you go to read the blocks, they're either there or they're not. You don't start reading blocks and get some of the new version and some of the old version. You're either looking at the UUID you're looking at, and the blocks are there, or you don't even know about the other UUID. This prevents all of those failures, random corruption of, I started reading this file and someone else started writing it, and now I'm reading what they wrote, or the other way around, or whatever. Whole class of problems completely off the table because those blocks are immutable. It also means that we can cache those blocks forever. We don't have to worry about any sort of write-through caching or write-back caching. Once we have read that block, we know it's not going to change. So we can hold on to it until the cache decides to eject it for memory, performance, whatever reasons. So what we've ended up with is 99% of the data that we store in RiakCS is immutable. There's those manifests that we change. We change which UUID a manifest is pointing to. We change what time it was written, that kind of stuff. But the manifest is a few kilobytes, maybe, usually a few hundred bytes. And all of the data in the file, that 4 terabytes, is completely immutable. So we don't have to worry about all of those mutability problems on the data in the file. Really scales back all of that surface area that we would have to worry about bugs in otherwise. So backpressure. There's an entire track about backpressure, and you should go watch all of the videos from it, because so far the talks have been great about things you should consider when thinking about backpressure in a system. In RiakCS, we're specifically thinking about how a writer might overwhelm a RiakCS node. So it would send a file so fast that that node couldn't write it into Riak to keep up with. And the problem that would happen would be that all of the data for the file would have to be able to fit on that RiakCS node. That doesn't sound too bad if it's a gig file or whatever. We have servers with terabyte of memory or whatever. But if you have lots of people connecting to the same server, and they all decide to upload 4 terabyte files, you wouldn't be able to store all of those terabytes in memory at the same time. So what we've done is, on the right side, we have an FSM. And the FSM decouples reading from the client and writing to Riak. If writing to Riak is not keeping up, we stop reading from the client. So TCP backpressure tells the client to stop sending data. This means that we never have to worry about memory pressure on the Riak node. We can say, we know that we can hold 4 blocks in memory outstanding right to Riak for 1,000 clients or whatever. And tune the settings to that and say, never allow more than 4 blocks outstanding in an FSM at a time. And that just prevents overwhelming the system. You might think that we're slowing down that client. He's going to have a worse time uploading. But it's actually kind of the opposite in a really parallel situation. Since people are sharing those resources, you actually do kind of want to slow down the really, really fast one that would overwhelm everyone else's operations otherwise. We also do the same thing on the Git side. If we have a really slow reader that we're sending data to and it's giving us TCP backpressure, we just stop reading blocks from Riak for a while. We read ahead such that we're not waiting to finish sending to this slow client before reading another Riak object, because that would give us some bit of latency in the middle of the file. We are reading ahead, but we read ahead only a certain amount, such that we're not using up all the memory that we would use for another request or whatever. So talking about requests, we may as well move on to Web Machine. Web Machine, if you're not familiar, is sort of a utility for easily describing correct HTTP. You might have heard Clacka dis REST earlier. In my opinion, he was talking about a thing that is hipster REST. It's not real REST. And so I'm not surprised that he dissed it, because it is kind of a hoax. But if you really want to do REST, Web Machine does this really great abstraction for it, where instead of like most things that say, this is a URL and it was a GET, please read from the socket and write out to the socket, Web Machine dispatches on URL to a what we call a resource module. It's an Erlang module that represents a resource at that URL. Web Machine then asks that module questions about the resource. And the questions are things like, does this resource exist? If not, Web Machine automatically sends a 404. So that function would have returned false. If it returns true, we proceed on. And it says, what kind of content type does this resource have? And the resource can say, actually, I can send these 3 types. Web Machine handles figuring out what type the client wants. If you're familiar with HTTP, the client can say, I only accept these types, but the resource provides these types, and there's a negotiation. Web Machine handles that. So basically, it's a bunch of functions that are properties of the resource. Web Machine figures out how to send the HTTP response that says, this is what you wanted in the correct format. So yeah, Web Machine is great. If you have a RESTful API, dispatches very nicely on URLs, uses GET and put in idempotent manners, uses post when it wants to go outside of things. Unfortunately, S3 is not quite RESTful to fit web machine really well. In particular, its URLs are a little strange. So you have this concept of a file, and the URL to the file is kind of the bucket name prefix in the file. But then there's also access control lists for the file. And it's the same URL with a little query parameter on the end that says access. So it's that question mark and an access. This makes web machine a little difficult to expose S3 because it wants to route both the file request and the file access request to the same resource module. So you would end up with a module that has kind of two sets of logic in every function. It's the set of logic for the file and for the access. And it just makes things really dirty. So what we do now instead is we rewrite requests. So kind of like Apache rewrite, that's what we named it after. When we get a URL, a request for a URL, we give the application that started the web machine an opportunity to change the URL. So RiakCS, it gets a request for a bucket foo. It rewrites it to buckets foo. This is important when it gets a request for the bucket policy at foo query policy. It rewrites it to buckets foo policy. This means that web machine will now dispatch those resource calls to two separate resource modules. So we can keep the logic for the bucket and the bucket access completely separate. And it's not interleaved in the file. And we do the same thing for files. We rewrite the buckets objects bar and bucket object bar ACL. Funny enough, this actually kind of gives you the inverse problem, where now there were some things that are common between files and file access policies. So if you imagine a very high-level view of the file, you might have had the authorization step the same for all of them. Who is it that's sending this request? You might consider that like the green part at the top. So now, instead of, we have these separate modules, but there's repeated code in all of them. And yeah, you can, define that in a function in a utility module elsewhere. But the way web machine works is it has defaults for all of those properties that it's going to ask your resource about. And if your resource does not export the function for that property, it doesn't call it, and it just gives the default answer instead. So for things like, does this resource exist, the default is yes. So you don't have to say, this resource always exists. What we ended up doing in RiakCS was building a way to do custom defaults. Basically, what we wanted to do was say, these are the things that every RiakCS resource is going to say in the same manner, but these are the extra things for this particular resource. So you might think of it as kind of like a dictionary merge of the functions in our specific resource with the functions in the general defaults resource. And in fact, there is a module in the repo right now. It's called something like, I don't know, RiakCS WM default or something. Or custom default. What it does is it exports every function that web machine might call. Inside that function, we look at the other module. So when you're dispatching from web machine, you have the URL and you have the module name that you're going to dispatch to. You also get an argument that you can send to the module at init time. We use that argument to send the other module name. So basically, all of our URLs now dispatch to this meta module, if you will, this custom default module, and then we'd parameterize it with the argument for the specific resource module. And we just use module info inside that custom resource file. That's exactly what web machine does. We just do it again. So web machine is always seeing that our meta resource module exposes this function, so we can override the custom default. I think there might be an outstanding request to just build this into web machine. So you would say, as one of the options when you start up, use this module as the custom default. I haven't been watching closely enough, so I don't know what that's named, and I can't tell you where to go look. But it's a useful thing. It means that we don't have that duplicate, authorize step in every single module. It's in one module. We don't even have to have what do they call it? A stub that calls out to the other module. We just have, we do it the other way. Oh, testing. Something that you have to do in everything. I was talking about how we want as few mutable places as possible, as much immutability, so we don't have to worry about what's going on. But those manifests, those are mutable. And if you know about Riak, you know that it's possible for two clients to write to the same manifest at the same time. Two people might decide to overwrite the same file at the same time, and you'd end up with two manifests. So when you read them back, you get both of these manifests. Riak doesn't just throw one of them away. It says, hey, there was a conflict here. You tried to do two things at the same time. Which one was right? What we did in Riak CS was define a function that takes two manifests and says, this is the correct one. It uses a timestamp and the state of the file, whether it's still being written or whether it's finished or whether it's being deleted and that kind of stuff, to decide which manifest is the correct one. But trying to decide whether or not this resolve function was right required some testing. And what we really wanted was this resolve function to be deterministic and give the same answer no matter how it got the requests. It needed to be both associative and commutative. We needed to know that if the list of manifests was manifest A and manifest B, and it chose manifest B, that even if we gave it the list manifest B, manifest A, the reverse order, it would still choose manifest B. Because you don't want one Riak node to reply faster and get the opposite order, and thus have one client see one version of the file and another client see a different version of the file. If you remember math class, associative and commutative is basically, you can add a string of numbers in any order, grouping them however you feel like. If you're thinking about it functionally, it's the same as folding left through the list and folding right through the list being equal. So I was talking about Erlang Quick Check. What Erlang Quick Check can do is generate those manifests for us. It can generate a spew of random manifests, and we can just have it generate that. We've coded in like this thing's a timestamp and this thing's a UUID and this is how you generate those. It'll just generate random ones, and then we, in the property, just say assert that fold L on all of these manifests with our resolve function is the same as fold R on all of these manifests with our resolve function. Yes, it means that we're not testing specific corner cases, but actually thinking of all those corner cases in a large application that has many knobs is a really hard thing and a really annoying thing to have to sit and type all the time. So we just have EQC generate tens of thousands of rounds of two manifests and one manifest and five manifests and et cetera, and we just let it run for 10 minutes, an hour, whatever. It's kind of it's random testing, and it works really well, actually. It's found some good bugs, and we've fixed some stuff. So back to backpressure. I was talking about HTTP 503 and how it's sometimes OK to say, no, you can't do that right now. We were talking about slow writers and fast writers and slow readers back then. But we also have the case where we're going to have many clients connect at the same time. And a cluster can handle 10,000 clients connecting at the same time. Might not be able to handle 20,000 clients connecting at the same time. If you let it do 20,000, you might get really slow requests for some of those. And you might get really fast requests for some of those. We kind of pride Riak on being extremely predictable. So we'd rather have the case where maybe not all 10,000 are going as fast as possible, but they're all getting about the same rate. And from 8,000 to 10,000, it's still about the same rate. And you don't suddenly get to the point where your rate is much, much slower, 5 times slower. We'd rather have it slow down a little bit, and that's fine. And we'd definitely rather not have some requests be much slower than other requests. So we learned to say, no, there's too much going on. I can't service your request right now. And the easy way we do that is to pool our connections to Riak. So instead of every request connecting to Riak itself and asking Riak for what it needs, we have a pool boy pool of Riak connections that we use over and over and over and over and over again. So when a RiakCS request starts, we try to check out a client from the pool. If we can't get the client, we just say, no, you can't do that right now. Getting the client is the first thing we do, and we just return from that web machine property that says, no, this service is not available. And web machine automatically sends the 503. Like I said, this helps a lot. And the thing we do that is a little bit extra is that we have separate pools for separate kinds of requests. So in RiakCS, we can write a file, we can read a file, or we can list all of the files in a directory or a bucket. Reading a file is, pretty lightweight. We can just plow through that. Writing a file might be a little more, resource intensive. It takes more time to get stuff onto disk than off disk. Listing the files in a bucket is something that can be very expensive. We kind of have to ask most of the Riak cluster instead of asking just a few nodes for some information. And waiting on all of them takes a long time, and all of them doing stuff means that there's more load on the cluster. So what we've done is we've made one pool for reading and writing data to Riak as the files, and one pool for listing those files from Riak. So when we get a GET request, we check out from one pool, and a list request checks out from a different pool. And we can change the sizes of those pools. So we can have a really large GET and PUT request pool, so we can have lots of those going on at the same time, and a really small list pool. So those are automatically held back, so we don't have a whole bunch of those active all at the same time. It means that we get a little bit more predictability. We don't have suddenly a whole lot of list things keeping anyone from reading any files at all. And the last topic I'd like to talk about is record versioning. I know people kind of dive into Erlang records and then realize they're not what they thought they were, and they're kind of a pain, but it's really great because you can pattern match on them, and that makes your code really clean, really fast. In RiakCS, it's a long-running app. People don't start up a RiakCS cluster and store some data in it and then throw it away and start up a new one. Well, I mean, they do during testing, but once they're in production, that RiakCS cluster stays around for months, years, whatever. So we end up, every time we have to roll out a new RiakCS version, there's a chance that we might have to change, for instance, the manifest object. And our manifests are stored as term-to-binaried Erlang records. So if we read something that an old Erlang CS application wrote, we might get an old record version. And if you know how records work, that means our pattern matches will no longer match. You change the name of the record, and that tuple no longer matches, or you change the size of the tuple, no longer matches. So what we have to do is upgrade those records before we can use them. We could have, all over the code base, this is how you deal with version 1 of the record. This is how you deal with version 2. This is how you deal with version 3. Instead, we defined an upgrade function that takes version 1 and upgrades it to the latest version. It looks basically just like this. Version 1, upgrades. It can either upgrade to version 2, and that's why it calls itself recursively. And then version 2 can upgrade to version 3, or we can write the code to upgrade version 1 directly to version 3. I think we've done both at this point. I know I've done both in other applications in the past. And basically, once that upgrade function sees the latest version, it just returns it. It's really simple. So then in the read path, we just immediately call upgrade as soon as we get the result. I was talking about how we might get multiple manifests back that conflict with each other. We upgrade all of the versions of the manifest and then run the resolve. This means that not even the resolve step needs to know about other versions of those records. It's only in the upgrade place, in the upgrade function, that we need to know about all of the versions of the records. Resolve doesn't need to know about it, and everything downstream from resolve doesn't need to know that there's any sort of conflict on the message. We have this nice path that just narrows down what we might get, and all of the rest of the code is dealing with one manifest that is the current version. Makes it really easy. This is a list of people at Basho that have contributed to RiakCS so far. this slide was made just before we open sourced it. So it's missing all of the people outside of Basho that have started to contribute to RiakCS. And we're really excited about those, but I didn't have time to do this. This is actually Reed Draper's slide deck, and I thank him profusely for letting me borrow it, because it meant that I didn't have to make 2 slide decks for this week. But these are some people you might go harass if you want to know more about how RiakCS works. But that's actually all I have, and I'm happy to take questions if anyone has any. Right here in the front.
A couple years ago, I was making a homemade system which is very similar to what you do. Did you consider using SHA hashes of content as keys to file pieces?
So we did, actually.
Yes, you have to ref count to garbage collect them, but you get nice property as saving space.
That's absolutely true. We actually did have an old version. Some of you may have heard of a thing called Luak. And it did exactly that. It didn't use SHA. It used Skirl, which was a contender for the latest. I'm losing the acronym right now. But yeah, we tried that out. And it was exactly the problem you described, that garbage collecting, when a file went away, meant that we had to do ref counting. Ref counting in Riak is hard because we can't atomically change that ref count. We might have a new file being written that's about to reference that object, whereas we might delete it out from under.
You could add a little header to each piece and then use regular conflict resolution on those little headers.
It doesn't work that way. We spent a lot of time trying to figure this out, and it's just not possible to atomically change that ref count or to bring something back from the dead if you accidentally deleted it. So there's inherent bit rot in that kind of system. So yes, it would have had space savings, but outside of the data warehouse, where you want to be able to store as much data as possible, and you have a lot of people storing redundant data, it's really not an issue. Most of our users are storing, things that every file is different, so they wouldn't get much utility out of that anyway. But great question, thank you.
Anyone else? Okay, give up for Bryan.
Thank you.